Okay, everyone, good afternoon. How's everyone feeling about Lab 2? Is anyone kind of feeling overwhelmed? Everyone got a good start? A little clunky in the way that we rolled that out, partly because the tools are pretty complex. There's a pretty steep learning curve. And also, we're having some lingering issues in the lab where some of the PCs in there don't seem to work well with the boards. I'm still trying to track that down. In particular, the projector PC doesn't seem to work at all. But some other ones are just fine. You know, you just plug it in and it's good. So I don't know if I suspect there's some bad USB ports in there, but I'm still trying to track that down. If you have any trouble with the board communication when you're in the lab, let us know. We're going to try to isolate which machines are the most problematic and maybe get Ryan to install some new USB cards in them. Okay, so for today, I'm going to finish the demo that I started last week, and then I'll try to tie up the interfacing material. I pushed quiz 3 back till the 20th, a week from today. So you have an extra week to take quiz 3, which will be on I2C and UART and JTAG. Okay, so we've got. Oh, and by the way, I didn't send an update or an announcement yet, but I vastly expanded the lab sheet, if you haven't looked at it for a while. So I added some more details about exactly how to set up the platform, as well as how to connect everything in there. Actually, this is the old version. Yeah, so there's a section here at the beginning that talks about all the modules you need in your platform design, and then there's a section under there that tells you what to connect. We had a group. This can be a little tricky because if you make a mistake in the connections, the system could fail in a way that's kind of inconsistent. So for example, I had a group last week who had the wrong clock connected to the SDRAM interface, the SDRAM controller. And it's an easy mistake to make because there's 2 clocks, and actually there's actually 4 clocks in total. There's the main 2, which is the sys clock and the SDRAM clock, and then there's also the incoming clock that comes in from externally, the reference clock, and then the outgoing SDRAM clock, right? Does it make sense? So make sure you've got the right clocks connected. What was happening was that because the SDRAM, the controller was on the wrong clock, it was kind of randomly crashing the board. And it took us a while to figure that out. Okay, so let's take a look at, so this is the platform design. Hopefully most of you have this set up already. So I've got the clock source, like I mentioned, this is just a port. That's the processor. Then there's the SDRAM controller. This is the clocks. This is PLL. It's an analog circuit that just cleans up the external clock. And the second clock source, the JTAG UART, and then I also added these outside of class, but you need them for the project. There's this PerformanceCounter unit and the LEDs. It's the parallel I/O to control the LEDs. So the way I have this set up now is exactly the way you want to have your system set up. You may have slight differences in the names of some of these components. And if you do, you might run into a compiler error when you compile in Quartus, but that's not a big deal because if you go back to Quartus and you say File, Open, and you go into the Neo System directory, which I'm already in, and you look at this inst. I think I showed this last time. Oh, sorry, that's not the right one. It is, but that's the VHDL one, that's why. That's the VHDL version. We want to look at the Verilog version. There's the Verilog version. Okay, so this is a template for being able to drop this Neo system into your design, into your top level design. And so the important thing to note here is that this is showing you what the ports are on the Neo system, which are not obvious by looking at Platform Designer. Does it make sense? Okay. So for example, notice there's LEDs export. You may have called that something different. And if you did, you just have to make the corresponding change over here in your lights.sv. Okay? Alrighty, so once you have the code generated in Platform Designer and compiled here in Quartus, which I believe I already have, then we can start with the software. Bless you. Okay, so to configure this guy, you just do neos2 configure soft, and so the soft file is in the output files directory, so it's just lights.soft. And see, now this is where you sometimes run into connectivity issues. Oh, that's working now though. Seems to be fine. So you can see that it went from blinking, now it's kind of, it's in configuration mode. And it's configuring. Okay, so we're good. And then, so we have the platform on here, but the software, there's no software on it. It's just the CPU is doing what right now? It's probably in some kind of infinite loop somewhere. Good question though. I don't actually know what it's doing. When you configure it and you don't have software on it, the CPU must be executing instructions. It might just be executing no ops or something. Okay, but so the point is we need to get software on there. So for that, I'm going to go in the lights directory, make a software folder, and I showed there was a few groups that I sat down with in lab and showed this, but I just want to make sure everyone's on the same page. So I'm going to go in the software directory, and then there's a command neos to create what is it again? Software create. I can't remember it. I got to check so it's in if you go to the lab sheet, it is right here, neos2 software example create. So I'm just going to copy and paste this because this is a long command. But the idea is that, oh, right, hold on. You just put everything on one line here. All right. Hold on, that should be a space there. All right. Okay, so we're saying that we want to create a software example, which is this Hello World program. It's kind of just like a template that we can start on. This name is Lights. I don't even know where this name is used, actually, because at the end of this command, you specify that the app directory is lights and the BSP directory is lights_BSP, which are just like two different software projects, like for example, that you would see in Eclipse if you were using Eclipse. And then you target the CPU. You can only target a specific CPU. So like in 313, one of the things we do in that class that we won't do in this class is do a multi-core system where you have multiple processors. But even if you have multiple processors, you still have to, each software project has to target a specific processor, because the only way to have, the only way to do true multi-core processing is have an operating system. Because this is bare metal, we have to target a specific CPU. And then the type is hello world, and then you have to point it back to your Neo system configuration file. Does that make sense? Okay, so I'll go ahead and do that, and then this will create lights and lights.bsp. If we go to lights, there's a script in there called create this app, and that will create all the files we need. Why wasn't that done in the last step? Unclear, just the way the scripts are set up here. It's also doing a build, so it's compiling a bunch of stuff. Notice it's running, it's scrolling by, but notice it's running neos2 elf G++ or neos2 elf GCC. These are the cross compilers. So you're compiling stuff for Neos on an Intel machine. Okay, now one thing that I want to point out here is that there's this lights BSP directory, and there's a script in here as well called create this BSP. If you make any changes to your hardware in the platform designer, and then you regenerate your hardware, make sure you remember to reprogram the FPGA, one, but also you have to run this create this BSP every time you change your hardware. So if you change anything in platform designer, you're going to have to rerun this, and it'll give you an error if you don't. But basically, this just regenerates the software layer for the hardware that you have in your platform. Make sense? Okay. All right. Okay. So now I'm going to go into Tmux because it's useful to have two windows open when you start writing your software for this. So the first thing I'm going to do is go to lights, and if you look in this directory, you've got lights.elf. That's the compiled. That's the binary. That's the compiled version of your program that you use to program the FPGA. Then there's lights.objectDump, which is the same thing except it's a text version of it. And then you've got hello world.c, and then there's a makefile. Now there are ways to modify, there are scripts that you can use to modify this makefile, but we're assuming that you're just going to put everything in the one, the hello world.c, all your code. So if we check that out, you can see it just says hello from Neos 2. Now obviously it's already built. If I type make, it says it's already done. So if I type Neos 2 download, I can just put lights.elf and it'll download that program to the board. And there it is. Now notice it says leaving target processor paused because I forgot to put -G at the end of that Neos 2 download. -G just says go. This time it says starting processor, and then this is the address. And if you go back to your SOP, sorry, I keep calling it, used to be called SOPC Builder, now it's called Platform Designer. If you go back to Platform Designer, you'll notice that you can cross-reference this address and it corresponds to your SD-RAM. Right? Remember we talked about like every peripheral has a range of addresses, so this address falls within the range of your SD-RAM. Okay, so it should be printing hello world, right? So if I type JTAG, Neos 2 terminal, can I just, yeah, that's it. You don't need any, okay, well there it is. It already printed hello from Neos 2. Apparently that message was queued from having run it earlier, right? So this is the terminal. I've never actually, I'm sure it's possible, but I don't believe I've actually ever set this up where I could type stuff in this terminal. I think in theory you can go, the communication is two ways. You could type messages for the CPU. We've always just used it for output purposes, but I think, like I said, there's an interrupt connected for that inside your platform. So in principle, you could have something that says press any key to continue, and then you can hit enter and have it go, like in the terminal, right? I just never tried it. Okay, so then the terminal kind of just hangs out until you Control-C and break it. All right, so the next thing I want to look at here is how do we talk to the performance counters. Now you might be thinking, I don't know if I made this clear last week, but why are we using a performance counter? What is that all about? The performance counter is it's designed to measure performance. And we use it in 3.13 a lot to basically measure how fast the code is running. And the whole objective in that class is to speed up code. In this class, it's going to be about controlling things and communication. But in this class, we're still going to use the performance counter as basically as a clock. So it's just a counter that counts every clock cycle, and it gives us very fine-grained measurement control. We can measure time down to a 50 millionth of a second because that clock ticks every cycle, and the clock is running at 50 megahertz, right? So we can measure the passage of time, which is very important for doing control, because when you do control, there's this assumption that you have this control period, and every so often you execute, you read the actuators, you calculate the outputs, and then you read the sensors, you calculate the outputs, and then you actuate your system. Does that make sense? Now in this lab, you're going to use it for controlling the duty cycle and the period of the pulse width modulation. And so that's the whole reason we've got that in there. Okay, so if I modify hello world.c, a couple things you want to add here to the headers. There's io.h, and then there's system.h, and then there's alt-types.h. Okay, so this is for printf. io.h is for the io read, io write. Those are just the io read and write intrinsics. System.h has your addresses in it for your peripherals, your base addresses. Of course, you could key them in manually if you want to, but then if they change in Platform Designer, then your code will stop working. And then alt types is for the basic types, the Altera types. You don't have to use that, it's up to you. So in other words, if you have alt types, you can use alt_u32 as opposed to saying unsigned int, right? Just a more explicit way. Generally speaking, when you do embedded system design, usually your types are more explicit than int and char and short. Usually you use some kind of a type library. Okay, all right, so then, so also, let's see, set tab stop equals 4. The other thing you can do is, set shift width equals 4. There we go. All right, so let me fix some things up here a bit. Okay, so now another easy trap to get in, well, first of all, your embedded software is generally going to run an infinite loop. If you ever did any Arduino type design with the Arduino IDE, you don't have to put a loop in there, but there's actually a function called loop, which you can fill in, and then that is actually in an infinite loop, but the loop is structured externally to that function. In this case, we have to put the loop in. One easy mistake to make is if I were to put this printf inside this loop, it breaks it, because it prints so fast that something happens, some buffer gets filled, and it destroys the state of the UART, JTAG UART. Now you might say, well, wait a minute, why don't they just why doesn't it just make the code wait for the buffer to clear? Unclear. I don't know why they didn't write it like that. But if you print really fast, it can cause issues. So I want to just print outside that loop, and then inside the loop. And one other thing I want to do is I mentioned that the performance counter needs to be started. Why? Again, I don't know why they chose that. They made that decision. To start it up, it's pretty easy. You just do IO write. Okay, now where do I write to? If you go inside the BSP directory and you look at that system.h, this is all the stuff, basically, these are just all constants, right, that are generated from your platform. So I usually have this open, and that way I can find the performance counter. You can see the performance counter base is right there. So then I can just paste that right there. So I can write to the performance counter, and then you have to tell it to go, and I forget how to do that now. I know I have it in here somewhere. Yes, here it is. Number 1. Yeah. Okay, so if you write to the now again, by the way, if you had renamed your performance counter in Platform Designer, it would have a different name. This is the default name. Performance counter 0 base. I'm going to write the value 0 to register 1. That just starts the counter. Again, why doesn't it just always start it? I don't know. It seems kind of strange, but you have to start it, and that would be outside the loop. So now another thing that's strange here is that one should really be a 4, right? Because the control registers, which is what I'm writing, are 32 bits. So if this is the base and my offset is there, then that shouldn't be a 1, that should be a 4, right? Well, it's multiplying that by a 4 for you, right? So this is like saying control register 1, but it goes up by 1, but in reality the addresses are incrementing by 4. And then the value 0 is just a magic number. You have to write 0 to that register to start the counter. That's something that would be in the documentation. I just pulled it out of the documentation. Okay. Okay, so that'll start it, and then once I'm in there, I also need a variable that I will use the alt types for. I'll say alt u32 count. This is a 64-bit counter. And then in order to read a 64-bit counter with 32-bit CPU, you have to read twice. You have to read the bottom 32 bits and the top 32 bits. So I'll say count equals IO read, performance counter base, and the upper part, I believe, is in 1. Yeah, it's in 1, right? Yeah. 1, and then I'm going to shift that to the right by 32 bits, but there's a catch. You have to typecast this 32 by Alt U64 because the compiler needs to know that you're doing a 64-bit shift as opposed to a 32-bit shift. And so you have to play this kind of this trick where, actually I think you have to typecast that too as well, don't you? Yeah, I do have it. I don't know, maybe try it with, I'll try it without it and see what happens. But so I'm reading address, control register 1. Now you might say, wait a second, hold on. You just wrote 0 into that same place, and now you're reading from it. Aren't you going to get 0? Well, in this case, the read and the write behavior of that register are different. Just because I wrote 0 to it doesn't mean I'm going to read 0 from it, because writing to it tells it to go, and reading from it gives me the performance counter, right? Which doesn't seem to make sense. But it's not a real register, in other words. It's kind of hacky, like the reading and writing action, when you read or write, it does two different things. It's not like you're writing a value and then you're reading that value back. That 0 that I just wrote to it is gone. It never actually got registered. It was just sent as a signal to start, right? It wasn't actually writing the value of 0, which is why now I'm doing an I/O read, which is the opposite of the I/O write to the same address, and yet I'm getting a different value. Okay, so I'm going to read that, and then I'm going to read that was the upper 32 bits, and then I'm going to read the lower 32 bits. So I'm just going to do I/O read, performance counter, I think that's in 0, and then I'm not going to shift that. Okay, hopefully that'll be good. Okay, and then finally, the last thing I want to do is I just want to put the counter value. I could print it to the console. Could do that, or I could use the LEDs to display it. I'm going to use the LEDs. So the LEDs is, you can use those with just I/O write, and I got to go back to my system.h, figure out what that, okay, I've got LEDs base in here, so I just search for LEDs. And then I'm going to put that in there. The LEDs just have, they just have the one register, so that will always be a 0. Again, this is offset, like which of the registers you want to write. And then the value I want to write is going to be count. Now the problem here is that, keep in mind that there's two problems here. Count is 64 bits and I only have 26 LEDs, right? So that's an issue. The other issue is that, remember, that counter is going up, is ticking up every 50 millionth of a second, right? So in order to be able to see it actually counting, I'm going to divide the counter. I'm going to take the counter and effectively divide it by some large enough number that it will have to increment a whole bunch of times before it'll tick up by 1 on my actual LEDs. So remember, it's 50 million. So if I take the count and I just shift it to the right by, say, well, if I shift it by 20 bits, that's like dividing it by 2 to the 20th power, right, which is about 1 million, right? So if I shift it by 20 bits, that'll effectively divide the counter value by 1 million. And so it'll tick up once every 50 times per second, once every 20 milliseconds, right? Maybe I should go a little more aggressive with that. I'll go 22, that's 4 million, 2 to the 22nd power, 4 million. So that would be incrementing, 5 times per second or so, right? So let's try that. And that's it. That's all I need. So, did I forget something? Okay. All right, so I think we're good to go. Now, I might have to typecast this with this Alt. I might have to put this Alt 64 here, but I'm going to try it without it. I'm just curious if it'll work. All right, so down in my secondary window, I'm going to go back to lights.bsp, and let's see how many errors I get when I try to build it. Oh, I didn't get any errors. Okay, wow, it actually, oh, it did say, there is a warning there, though, that says left shift count is greater than the width. Ah, well, there you go. So that answers my question. So it's saying that you're shifting by 32 bits and you only got 32 bits. The compiler is seeing this value as 32 bits. We don't want that. We want it to see this as a 64-bit value. So I am going to go ahead and just typecast that. That'll get rid of that warning. So Alt U64, and I'll put Alt U64 there. All right, so that should get rid of that warning. And okay, it's good to go. If you look at lights.elf, it should have the It should be February 14th, 2:49, so that's good. So let's give it a shot. Neos 2, download lights.elf. Let's see if it works. So it's downloading it. Okay, it is not working. It's not doing, oh, there it goes. There it is. Just took a little longer to get started. So you can see that it's counting up now by 200 milliseconds or so. Every 200 milliseconds it counts up, and now it's and it's going to use all 26. Now I had an issue earlier to, oh yeah, that's good. Yeah, see there's, once it counts up, once it gets to bit 8, it rolls over to the red LEDs, right? It's because we got the green here and the red here. Okay, any questions about that? Yes?
Just for our FPGA, the red does not work when we did that with ours, but we haven't really looked at it since then.
Okay, you want to double, there's a few things you want to double check then. You want to make sure that you've got, because there's several things that could cause that. One thing is in Quartus, you got to make sure you've got the red, well first of all you have to have an output for the, I don't know how well you can read that, but there's an output here for LED-R, and you have to have an output port for it on your top level design. You also have to actually connect to it internally inside your design. And the way I did it was the LEDs export, which is the port on the platform designer design, I connected to LED-R and G. Now I haven't shown this to you guys yet, but this is a system Verilog thing where if you use curly braces, you can concatenate two signals, even if you're writing to them, right? You can concatenate two signals even if they're basically effectively on the left-hand side of an assignment, which is what's happening here. You guys, what I mean by that is this LED's export is an output. That's how I had it set up. So this is outputting, and I'm outputting simultaneously to two signals in a way that where they're concatenated. And because there's only, I could have also created a separate LED-G and LED-R outputs from SOPC Builder, or I could have had each bit individually set up as a PIO too. Does that make sense? So you want to check that. You also want to check your code. Let's see, your C code. Make sure there's nothing strange in there. And of course, there's the SOPC Builder, the platform designer. Sorry, the LEDs. Make sure you've got the clock there. Actually, though, if it wasn't clocked, you wouldn't get any LEDs, right? It wouldn't just be the red ones. So, oh, I know what it could be. Actually, I just thought of this. If you double-click on that parallel I/O, which I called LEDs, the default value I think is 8. So if you didn't change that, then that would because there just happens to be 8 green LEDs. So that might have been. Okay, yeah. So I changed that to 26. Okay, no problem. Any questions? Any other questions? Okay, so you can also debug your code on the board. I won't go through that, but you know I've showed some. If you guys have questions about that, let me know. We can sit down and help you with that in the lab. There's also instructions on how to set up debugging in the lab sheet. Okay? And when I say debugging, I mean software debugging, like you can step through each line of code as it runs on the CPU. You can also do stuff, well actually, you know what, hold on, I bet I could really quickly show you that, something that's kind of cool about that. If I go to terminal, okay, so, where's my other terminal? Okay, so if I type Neos 2 GDB server -- TCP port 8888 -- TCP persist, like that, and then over here I can type Neos 2 ELF GDB GDB lights.elf, and then target remote localhost 8888. That should connect. Okay. Now, I think your last command, you said light.elf instead of lights. Oh, yep, you're right. I did. Thank you. Lights, target, remote, localhost. Okay. So yeah. So now. once I connected to the debugger, it froze the program at that line of code. Okay? But the neat thing about this is that once you connect to the debugger, you can read and write anything in the space, in the memory space that the NEOS has access to, including the LEDs and performance counter and stuff like that. So, for example, like say if I say set, and then I go back to my BSP, lights BSP, and I look at system.h, and I look for the LED. Okay, the LED base is right here. It's 10001040. Now I mentioned that you shouldn't use those numbers in your code, but in the debugger, it might be useful to, to do something like this, where you can just set values. So I can I can set like that star is a dereference. Hopefully you guys covered that in 240. So the star is a dereference. So the star means I want to set the location at memory address 1001040 to 12. So then I could say I don't know, FF00FF. So that should put 8 ones, 8 zeros, and then 8 ones on there. See? And then I get 8 ones, 8 zeros, 8 ones, right? So I can directly manipulate stuff through the debugger to the board. Of course, and I could read the performance counter if I wanted to as well with that. Except instead of set, you would just use print, right? The print command. Okay, any questions? Okay, great. All right, so yeah, I think all the information is in here. If you have any questions about the lab sheet or if I missed anything, let me know. I have the debugger in here, and all the commands you need to get going on that. Okay, so I'm going to try to finish up the remaining material here. Let's see, I think we got through UART, and we started talking about I²C. Okay, so we were talking about SPI. Yeah, so I think where we left off is SPI is a single master, possibly multiple slaves. But if you have multiple slaves, you run into this issue where you have the MISO. There's only one master, so MOSI isn't a problem because there's only one entity that can put a value on MOSI. But MISO has to be shared, right? And so the reason that's an issue is because SPI uses push-pull drivers, meaning that the chip is either going to pull the output wire up to VDD or pull it down to ground, right? And so if you have a conflict where one device, one of the slaves is trying to pull up and one of them is trying to pull down, then you short circuit. You get a short circuit. Unless you put in a tri-state buffer that allows you to cut your chip off from the connection, which obviously you'd have to do it for SPI, but a better solution, or another solution I should say, is to use this open drain style interface where you just, instead of having the pull up transistor there, you have a pull up resistor with a fixed resistance value, and then all of the devices that are sharing that connection on the bus have the ability to pull it down to 0, and if they don't do anything, it's just 1, right? And if you have multiple devices pulling down simultaneously, it's not a real big deal. It's not going to cause a short circuit because you're going to limit the amount of current flowing through because of that resistor. That's what that resistor does. Now the disadvantage of this is that you can never explicitly set the wire to 1. 1 is kind of its default value, which it will be set to if you don't do anything, right? So if no one's controlling the wire, it's 1. And if multiple drivers are trying to pull it up to 1 or set it to 1, then it's still 1, right? So that part gets a little weird, but it's nice for having it allows you to have a multi-master bus because you can have multiple devices on sharing one wire. So I²C uses that approach for both the two wires. So it only has 2 wires, SDA and SCL. Sometimes they have different names if you look in documentation or data sheets. But one of them is a clock, one of them is data. So CL is clock, DA is data. The pull-up resistor is where? Where is that? Is that something you have to put on? Usually it's external. Some chips will have it internal though. So you have to be aware of that when you're connecting chips, whether they have an internal pull-up resistor or you're expected to pull it up externally on your circuit board. So the objective is to have the bus be multi-master. It only requires 2 wires instead of 4, so it's a little bit more space efficient than SPI. The other nice thing it has that SPI doesn't have is an acknowledgement mechanism where every transaction has 2 parts, right? Address and data, right? Right, you guys remember that from SPI, it's the same way. Except with I2C, there's an acknowledgement that comes after both phases. Both the address and the data phase have an acknowledgement bit, which allows whoever is sending the address or the data to know whether the other side acknowledged it. Make sense? SPI is a little bit more tightly controlled than, I2C is more tightly controlled than SPI. It has standard bit ordering. It has standard speeds that it can run at. Unlike SPI, which is like, you can use any bit ordering you want. You can run at any speed you want. It's just it's not as tightly defined. Whereas I2C is a little bit more standardized. Also, it doesn't have any of that CPUL and CFA stuff. Or you don't have to have channel settings. There are some channel settings, but it's not like SPI where the timing information is actually part of the settings, or UART where you have to have you have to agree on the speed, and and all transfers use this programmed I/O behavior, or the read or write transactions. Okay, so the basic idea with this is that with SPI. I emphasized in class that SPI uses the clock edge to clock bits, right? So we looked at when does the first bit come in? On the falling edge or the first falling edge of the clock or the first rising edge of the clock? That's where that CPUL and CFA thing came in. I2C on the other hand is not edge triggered for the data is not synchronized to the edge of the clock. Instead, it's a level sensitive system where the data bits are held constant for as long as the clock is high. So whenever the clock is high, you don't change the data. You allow the receiving end the time in which the clock is high to grab the bit. Does that make sense? So it's level sensitive in terms of the clock. So I'll come back to that in just a minute. So it's multi-master. So whoever wants to take, whatever device on that bus wants to perform a transaction, basically just grabs the bus. And the way it does that is it initiates a start bit, and then it sends an address, a 7-bit address, and then there's a read or write bit. Okay. Now the presumption is that all of the potential slaves on that bus are monitoring that, and if any of them matches that address, then they will then recognize that whoever's got the bus is addressing them, and they will acknowledge. So in total, there's 9 bits. There's 9 bit slots that are in this header sequence. Unlike SPI, remember there was 8 bits. Now there's 9 because there's 7 address bits. Now the start, by the way, the start is not a bit, so I'll come back to that in a minute. There's 7 addresses, 1 read-write flag, and then 1 acknowledgement, right? And then there's 8 data bits and an acknowledgement, so there's another 9. So there's 9 and 9. There's 9 in the header field, the 9 in the header part, and 9 in the data part. So there's 18 total bits that go through on these transactions. Make sense? Okay. So now you might say, well, wait a second, hold on. Wait a minute, how do you acknowledge if there's only 2 bits? There's only 2 wires. How do you acknowledge? There's whoever's taking mastership of the bus obviously has to drive the clock because it's a synchronous protocol like SPI, and then they're going to send this header data through the data line. So how does the acknowledgement come back? How is it acknowledged? Well, it turns out that whoever takes mastership of the bus drives the clock, and they start out by driving the data, but during the transaction, the data line changes hands. It changes drivers. So initially, the master will send the address and the read-write, and then the target of the transaction will then seize control of the data wire and then do the acknowledgement. And then if it's a read operation, where the target is supposed to be providing data, the target will hold on to the ownership of the data line and send 8 bits back, at which point the master will seize control and do his acknowledgement. Does that make sense? Right? On the other hand, if you're doing a write operation, the master will send the header field, the target will acknowledge, then the master will take back control of the data and send the actual data value, and then the target will take control again and acknowledge. Does that make sense? So the master side is always responsible for driving the clock, right? But the other wire changes back and forth depending on who needs to use it, using that open drain style interface. Now there is one exception to that. There's something called, I lost it, my memory's shot. There's a feature of SPI where the slave, if the slave wants more time, it can take the clock and pull it down and extend. It can stall. It can make the master wait. It's called clock stretching. That's what it is, clock stretching. So there is a potential, I don't generally cover that in this class, but there is a potential for the slave to grab the clock and take control of that just for the purpose of delaying the master. But normally that doesn't happen. That's just a special case. Generally speaking, the master has the clock and the data line goes back and forth. Okay, so what about the start and the stop bit? The start, okay, so the clock I mentioned is level sensitive. When the clock is high, that's when the bits are supposed to be conveyed. Not on the clock edge like in SPI, but when the clock is high. The caveat of that is that the data line should never change when the clock is high. Whenever the clock is high, it's like, red light, green light. Your clock goes high, you have to freeze the data, right? The exception to that is the start and stop bit, which explicitly are violations of that rule, but it's meant to represent a special case of starting and stopping. So the start bit is when the SDA is pulled down while the clock is high. And again, normally you would never change the data when the clock is high, but this is the start signal, right? Likewise, the stop signal is when we go from, we put the SDA high while the clock is high. Does that make sense? So basically, anytime you change the data when the clock is high, that's going to mean a start or a stop. And it's not really a bit, like with UART. It's a signal. It's a condition. It's an event, right? Does that make sense? It took me forever to remember that. Because it's kind of just, the best way to remember it though is to just say, under normal conditions, you don't change the data when the clock is high. Okay, so here's what the transaction looks like. So it's an open drain. So remember, if no one's talking, the default state of both those wires is going to be a logic 1 because of that pull-up resistor. No one's pulling down. It's just got, you basically see the voltage that's between these signals and ground are all the pull-down transistors, which all have about a mega ohm of resistance when they're turned off. So you have a bunch of mega ohm resistors in parallel to ground, but to VDD you have a 10,000 ohm resistor going up. So the effective voltage here is going to be very close to VDD. You're going to get some losses over that pull-up resistor, but it's going to be, if it's a 5-volt system, it's going to be 4.9 volts, something like that. So it's going to look high, right? They're both high. No one's talking, they're both high. Now remember, I said that you don't normally change the data when the clock is high, so when I want to start, I want to take mastership, I'm going to pull the data down while the clock is high. Now what's supposed to happen now is, first of all, everyone's supposed to acknowledge that, the bus is now being used by someone. But if I try to take ownership at the same time that someone else tries to take ownership, I'm supposed to be able to detect that and then bail out. Now, how do they do that? I have no idea. I don't know how that works actually. Like, how do you know? Like, if I pull the data down, how do I know that I pulled it down slightly after someone else pulled it down? Because either way, it's down, right? It's been pulled down to ground. I don't know, but there is a collision detection system that's supposed to be in place here, where if two collide, two entities try to take mastership at the same time. But anyway, once that happens, now I've got the start. At which point, the master will set the bits, each of the 8 bits, right? There's 7 address bits and the read or write flag, and it sets the bit, and then it brings the clock up, and then back down. Right? So notice how the clock, the way this is drawn, you measure these bits during when the clock is high. Not the edge, it's a level now. We're talking about the level sensitive, right? Okay? And so you've got 1, 2, 3, 4, 5, 6, 7, 8 bits, okay? Now, what's not shown on this diagram, well, it is, I tried to call it out there, but basically, once the master gets done with that, the slave, whoever is at that address, has to go into action and drive the data down as an acknowledgement, right? So it drives it down, then it waits for the master to raise up the clock. It holds that down until the clock then goes back down, right? So the target of this transaction has to pull that down to acknowledge. If it doesn't acknowledge and the master sends the clock up and brings it down, then that's a knack. That's a not acknowledge, in which case I'm done. I give up. No one's listening. Right? That's the idea. So so the master yields control. Now you might say, what does it have to do to yield control? Nothing. It just doesn't pull it. It just doesn't pull. It doesn't pull data down, and it also kind of uses the data as an input now. All of a sudden, it was an output. Now it's an input because I want to see who acknowledges. Right? I'm outputting here, and now I wait and I use it as an input for 1 clock cycle, and I have to clock it. Okay. Now I mentioned that there is that clock thing where the slave could take the clock and drag it out and not let. But yeah, like I said, we won't cover that. Okay, so then once that happens, then I have to do my write. If I'm the master, I'm going to send out 8 bits that I'm going to write. If I'm the slave, I'm going to send 8 bits back. So someone else is in control here, or depending on if it's a read or write. And then there's an acknowledgement by whatever side didn't send the data. At which point the master will issue the stop condition, which is where the data changes when the clock is high, which is not normally allowed, right? So normally when the clock is high, nothing changes on the data line except at the start and the stop. Okay, does that make sense? Okay. All right, so here's an example. So what's going on here? Well, I mean, I can see the start here and the stop there. If I want to look at the bits that are transacted, basically I just look at when the clock is high. So it's going to be 1, 1, 1, 1, 1, 1, 1, 1, 0, and then 1, 1, 0. Right? So I think that's the read or write bit right there. Am I right? Yes. So master sends 1, 1, 1, 1, 0, 1, 1, 0. This is the 9th bit, so that's the read or write. And in this case, if it's 0, that means I'm writing, which means that these other bits, well, first of all, it means the acknowledgement is the next one from the slave, and then I transfer over and I send 8 more bits on the master, and then the slave will acknowledge at the end of that. You guys with me? So there's 18 total bits that are sent. Okay. Okay. So this is just an example quiz question. What's the stop condition of I squared C? It's the clock being 1 is the key here. Clock is 1. if you change the data when the clock is 1, that means something special. So rising edge of SDA when the clock is 1. Did I get that right? Yes. A. Okay. Yeah, so this just kind of summarizes this again. In a read, the first 8 bits are from the master, bits 9 to 17 to the slave. Why 9 to 17? Well, that's the acknowledgement plus 8 bits for the data, right? And then bit 18 is the master. If it's a write, first 8 bits are the master, bit 9 is the slave, bits 10 to 17 are the master because that's the data you're pushing out, bit 18 is the slave. This is starting at 1, by the way, not at 0. Make sense? Okay. All right, well that's it. That's it for I²C. Any questions about that? Okay, so the last one, and by the way, there's a ton of these types of protocols. I'm not trying to imply that SPI and I²C are like the only ones, and UART. There's a lot of them. You would be surprised. Even on this board, even on this DE2 board, there's, we looked into it, and there's the SD card. You can communicate with the SD card with SPI, and you can talk to the controller for the sound chip in I²C. But then there's different, there's an SD RAM, there's a flash interface, there's, I forget what there's a video interface. So these are just examples to give you an idea of how these interfaces can be designed. The last one we're going to look at is called JTAG. JTAG is pretty cool. It's been around for a while, and people these days just kind of take it for granted. JTAG is yet another type of serial protocol like the ones that we've been using, bit serial, SPI and I²C are bit serial. You send 1 bit at a time, and then at the end point they get assembled into a parallel value. However, this one's a little bit different, the way that it works. It's comprised of 4 wires like SPI, with an optional 5th one called test reset. But the main 4 ones are the ones that are important to understand. There's test data in, TDI, test data out, TDO, and then of course there's a clock, test clock, and then there's test mode select. So this works a little bit like SPI in the sense that it acts like a shift register where you shift bits through one at a time. So bits are shifted out of the master and into the slave, and out of the slave and back into the master. It's essentially how it works. It's a big shift register. JTAG, though, is used for basically 3 things. It's used for debugging, so that GDB thing I showed you when I lit up these lights in this configuration, that was done over JTAG. So the GDB works over JTAG. The UART, which is a little console thing, that operates over JTAG. It's also used for it was originally designed for boundary scan. Believe it or not, the original idea with JTAG was to test circuit boards. You would take, right after the ball grid array came out, so chips, I don't know if you guys ever looked at a circuit board, but you've got different types of components on here, depending on how they're mounted. Some of them are through hole, like the aforementioned op amp, you stick it's a dip package that goes in, it's got little spikes on the bottom, it goes through holes on the board. There's other stuff that's surface mount, and among the surface mount devices are the most aggressive ones of those are the BGA packages, ball grid array. That's what this FPGA uses. There's an array of pins on the back, and you have solder paste on those pads, and then typically a robot would take the chip and it would align it with the board and then lower it down on top of the pads, and then you put it in an oven and you cook it, and that melts the solder paste, and that creates the connection between the balls are actually solder balls. That's why they call it BGA. There's not actually balls after it's cooked because the balls melt and they turn into just a solder joint, right? The problem is that once you put the chip on there, you guys can't see any pins on this thing, right? I mean, you see the FPGA, right? It looks like this black ceramic package, but you don't see any of the pins, and you can't reach any of the pins with a probe. So the only way to tell if this thing is on is if you have the ability to test every pin somehow. And that's what JTAG was used for. JTAG was this thing where you would shift in bits for all of the pins, and then you could use that to test whether you had a good solder joint for these BGAs. But then they eventually they co-opted it. Now they use it for, it's basically a side channel that allows you to get data in and out of a chip for a variety of reasons. In our case, mainly for debugging in console. So anyway, it's a big shift register is the idea. It's 1 bit at a time, so it's very pin efficient, but it's slow. Much like I2C and SPI, it's very efficient in terms of the number of wires, but it's really slow because you have to go 1 bit at a time. Okay, so how does it work? Basically, you create what's called a JTAG chain. Oh, this is also how the FPGAs are programmed too, by the way. And so you can have multiple devices on this chain, and they all form, there's a big shift register inside each device, and then the devices themselves act like a big shift register. So you have the test data in coming in one device is then transferred, you get the data coming in there and data coming out of test data out, which then is passed to the next test data in, and then on and on. So it's kind of like the daisy-chained SPI configuration that we talked about for multi-slave SPI. However, there's this TMS, test mode select, and this connection is actually fanned out. So instead of being arranged as a daisy chain, the TMS connection is connected individually from the master to all of the slaves, or all of the things on the chain, and as well as the clock, right? So the master drives the clock and the TMS, and then these things are just shifted through like daisy-chained SPI, right? Now, what is TMS for? TMS is the way that you can tell the devices in the chain what mode to be in or what they should be doing. But it's done through bit serial. So the way it works is they have this 16-state machine where basically most of the time you spend in this test logic reset state. But if you want the devices in the chain to do something, you send a sequence of single bits out, and the pattern of bits allows you to go to whatever state the master wants all of the devices in the chain to be in. So for example, if you're in test logic reset, as long as you keep putting 1 out on the TMS output and clocking, it'll stay in there. But if you put a 0 out there and clock that, you go into this run test idle, and you set TMS to 0, you'll stay in there. Or if you set TMS to 1, you go into this select DR scan, at which point you can come down eventually to the shift data register or the shift IR register. And those are the two important ones. So what I'm trying to say is that as the master, if I want all of the devices in the JTAG chain to go into the shift DR register, the data register, I would clock in the following pattern of bits. I would put in 0, then 1, then 0, 0, and I would keep it in 0 for as long as I wanted to stay in there, at which point I would switch TMS to 1 and clock it, and then I go in this exit state. Does that make sense? No matter what state I'm in, if I set the TMS to 1 for at least 5 cycles, I will get back to this start state no matter what state I happen to start in. So it doesn't matter where I'm at. Like say I'm in this state, if the TMS is 1 and I leave it at 1, I'll jump to here, and then I'll jump to here, here, and then back to here, right? So there's a pathway. So generally when you start up, assuming you don't have this test reset pin, this test reset, like if you don't have this test reset optional wire, then all you have to do to reset everybody on the chain is to just put the TMS to 1 and clock it 5 times, and they'll all be in this state guaranteed, even if they kind of start up in a random state. Does that make sense? Okay, so what's the purpose of these states? Well, there is a data register and an instruction register. So when you do a JTAG transaction, you have to send an address, much like you do with SPI and I2C, but the address is clocked into the instruction register. So you have to go through 2 phases. You have to tell every device in the chain that you want to put an instruction in which case you go through the proper sequence of TMS values to get all of the devices on the chain into the shift IR state, at which point you just shift values in through the test data in, and you can shift values into that chain. Does that make sense? And that'll put an instruction in. Then when you're done with that, that instruction acts as an address to a register on the JTAG device, at which point you do the same thing, but you go into the shift data register. And this allows you to shift bits in, and that allows the device on the chain to shift bits out. So every time, so what I'm trying to say is every time you use this FPGA, you use the console or use the GDB debugger, or you program the FPGA, it goes through this sequence to actually perform these, to get data in and out. Make sense? Okay. Alrighty, so yeah, so the TMS sequence is 11111 goes to the test logic reset from any state. 0100 enters the shift DR state. Once you get there, you leave TMS 0 to stay in that state for as long as you need to shift bits. So from that data state, there's 1 registers the value. So once you're in this state, if you go 1 and then 1, it updates the data register. So there's a 2 clock sequence to register the value. Once you shift it in, you commit it. And then the instruction register is 01100, gets you to the shift instruction register. You keep TMS 0 to stay in that state. And then from the shift IR state, you put a 1 to register that. So 1 and then 1. Shift, wait, exit, no, sorry, here, 1. Shift IR 1, and then 1, which goes to the update instruction register. Does that make sense? So there's the shift DR and the shift IR are the states where you're shifting values in, and then in order to latch them into the actual device, you do have to go through an extra 2 cycles to go to this update DR or update IR state. So what is the point of this? It's very similar to SPI, except it has a separate control signal to control what's going on in the transaction, as opposed to having basically a packet format like I2C and SPI has. Okay, so basically the idea is when you bring in the instruction register controls a MUX, well, actually a DMUX and a MUX, such that the data coming in through TDI will go into whatever one of the registers that you told it to go into based on the instruction. Now there's 4 main ones. There's an ID register, which identifies devices on the JTAG chain. So for those of you that have programmed the FPGA using the programmer in Quartus, how many of you, the graphical programmer, have any of you done that? I know at least one group did. Some groups just open up the programmer, and what I mean by that, by the way, is I have Quartus open. I can just bring it up. So if you go into Quartus and you hit, there we go, this button. Yeah. So this programmer, this is normally how you program it. You know, you just, there's the lights.soft and you hit start. I've been using the command line, you know, the Neos 2 configure soft, but this is the graphical way to do it. You can see in this programmer, it actually shows the JTAG chain graphically. There's the FPGA, there's the TDI, and there's the TDO. Now, on the other hand, if you were to switch, there's a switch on this board down here in the lower left-hand corner. If you switch this to program mode, then it actually changes the JTAG chain, and it'll put the flash chip on the board in here, so you can program the flash. That's how you make it so, you know, when you turn it on, it comes up in that blinking configuration. If you wanted to change that, if you wanted to permanently alter the soft file that's on the flash chip on there, then you still do it through JTAG, but you have to change the JTAG chain configuration. For whatever reason, they don't have the FPGA and the flash chip on the same chain. I don't know why they didn't do that. But anyway, there's TDI and TDO. Any questions about that? Yeah, so normally, you know, just like there's the USB blaster, and I would hit start, and I can't do it because I got the debugger open, but if I close the debugger, I would be able to program it. Okay. All right, so that's JTAG. So there's a couple variations on some of these. Some of you might have heard of CAN, which is the Controller Area Network. That's the one used in vehicles. It's actually a variation on I2C. And then you might have heard of I2S, which is a digital audio protocol, which is also a variation on I2C. They're not identical. There's some differences, but in fact, I2S is 3 pins. But there's some. The point is, there's other protocols built on top of I2C. And then finally, I just have a comparison slide between the 3 that we talked about: I2C, SPI, and JTAG. I don't have UART on here, but I2C is half duplex. There's only one. You can only one entity can send bits at a time, whereas SPI is full duplex. You have bidirectional, except we hardly ever use that capability with SPI. JTAG is also sort of full duplex because it's got that shift register, except it requires a lot of cycles to shift all the values around the daisy chain. The performance, I2C is generally less than 3.4 megabits per second. SPI and JTAG have no limit because there's no defined limits in the spec. It'll run as fast as your wires will allow you to carry the data. I2C is an open drain. SPI and JTAG are push-pull style drivers. The word size is 8 bits on SPI, but there's no restriction. As a matter of fact, on JTAG, the different registers are different sizes. So there's a bypass register that's 1 bit, an instruction register is 5 bits. The boundary scan would be the data register is 14 bits, and there's an ID register that's 32 bits. So the registers are different sizes. But I2C, it's defined as a fixed 8-bit, although SPI normally is 8 bits as well. Addressing with I2C is also fixed. Every device has a fixed address that's defined by some kind of consortium, kind of like the USB ID. Whereas SPI and JTAG, there's no. It's not codified. The pins, 2 pins for I2C, 4 for SPI, and 4 minimum for JTAG, although there's some optional pins. And then I2C is the only one with the acknowledgement. All right, so that's all. That's everything for this lecture. Any questions? Okay, so those are all the protocols we'll cover. Hopefully, having seen those, you will be able to fairly easily pick up any other ones that you need to learn. In the meantime, we've got quiz 3 is due in a week, and we'll be back in the lab this week to work on Lab 2. If you have any hardware issues, let us know. We can walk you through it. Once you get the hardware set up, the idea is that you just put code in helloworld.c to implement the desired behavior. We were deliberately vague on how to actually implement the PWM in your code. That's something that's the part that you're going to put in. We talked about PWM, and it's basically a fixed period, and then there's a duty cycle that vary. And we showed you how to use the performance counter to basically synchronize things happening in your code. But from that, but to take that and build a PWM, that's the objective of Lab 2. And it's only requires a few lines of code, but it's of course tricky to figure out how to structure those. Okay, any questions? Okay, great.